Thank you very much, and I would like to thank the organizers for inviting me to this wonderful conference. I have a great time. And so I will start my story back in the 1930s, so long ago, when Erdős and Turán stated this beautiful conjecture. It's a very simple looking conjecture. It asks if every dense subset of the integers contains an arbitrarily long arithmetic progression. Now, it looks like an infinite statement. Here, density means positive lower density, but it is actually a finite statement. The finite statement says that for every epsilon and k, there is a large enough n, such that if you take an at least epsilon density subset of the first n integers, first n natural numbers, then it has a non-trivial k-term arithmetic progression. So almost 20 years passed until Roth, the Fields medalist Roth, proved the case for the three-term arithmetic progressions using Fourier analysis. And quite strangely, this Fourier analytic technique did not work for the higher case, which will be important later. So I will come back to that. And then another 20 years passed until Endre Szemerédi finally proved the whole statement using combinatorial methods. The methods were actually very far-reaching. Endre told me himself that the seeds of the famous regularity lemma were already in the proof. Actually, the proof did not use the regularity lemma, as some people believe, but the seeds were already there. So in between 75 and 78, he formulated this fantastic structure theorem for dense graphs, which is one of the most powerful tools in combinatorics. But the story didn't stop here. In 1977, Fürstenberg gave another proof for Szemerédi's theorem using not Fourier analysis, but another analytic technique, namely dynamical systems. And his proof was based on a correspondence principle which connected arithmetic combinatorics with the properties of dynamical systems. And it basically acts like a limit approach to arithmetic combinatorics, what he did. So this is kind of a first example in a bigger subject where you can take limits of things and then analyze them by looking at their limits. So by the end of the 20th century, many tools in mathematics were developed inspired by this simple-looking question. So let me just summarize the moral of this. So Fourier analysis helps in the analysis of additive structures, but it has its limitations, as I said, because it only worked out for the three-term arithmetic progressions. Second thing is that, what I wanted to mention is that this regularity lemma actually leads to another quite simple-looking proof of Roth's theorem via the so-called triangle removal lemma. So what is the triangle removal lemma? I tell you it in an informal way. So if you have typically it's interesting for dense graphs, and you have a dense graph where the triangle density is low, keep in mind that the triangle density is normalized by n cubed. So the triangle density is small, then you can remove a small fraction of the edges, which is normalized by n squared. That's why it's surprising that you removed all triangles. So there are the union of those triangles can involve many more edges, but you can still find this small edge set which removes all the triangles. Now that provides a new proof for Roth's theorem. So also an important thing is that this connection to dynamical system, I wanted to tell you a little bit more about that. And this is based on the concept of a measure-preserving system. Take a probability space. It could be a standard probability space. And the measure-preserving map. Out of convenience, we often assume that both T and T inverse is measure-preserving. And so it's an invertible transformation, if you like. And then Semeridis theorem corresponds to this recurrence statement that if you have a positive measure subset of this probability space, then, and you fix some k, then you will find some n natural number. Obviously, you may feel that this will correspond to the difference in an arithmetic progression, such that if you iterate the nth power of this transformation and you intersect the image of S with this, then it has a positive measure. This is the recurrence statement, which turns out to be actually equivalent to Semeridis theorem. So very importantly, if you want to understand, study measure-preserving systems, one of the most crucial concepts is the concept of a factor. Now this is, I'm not going to, actually I'm going to define it precisely. A factor is just a sigma algebra, which is invariant under this measure-preserving transformation, a subsigma algebra. But so if you want to think about it, it's basically the same concept of factor, which is everywhere in algebra. When you take a factor of a group, divide the group into equivalence classes, which are consistent with the group operation. Now, this is basically the same thing. You can factorize measure-preserving systems, and it turns out that if you want to understand certain properties of these systems, it's enough to study certain factors. So that's the tool, which is absolutely crucial. And for example, Fourier analysis appears in some sense naturally in ergodic theory in the study of a very specific factor, the so-called Kronecker factor, which is, by the way, generated by the eigenvectors of T. And those are Fourier functions of a certain abelian group, a compact abelian group, so the factor can be given this structure. And it turns out that the three-term arithmetic progression case actually just related to that Kronecker factor. So it already shows that these things, how these things are connected, the Fourier analysis, ergodic theory, and all these things. Okay, and now I arrive to this slide, which is one of the main slides. I like to call it the higher order revolution in mathematics. So after all these developments around 2000, motivated by the works of Roth, Semeridi, and Fürstenberg, there was a sequence of 3 breakthroughs roughly at the same time. A breakthrough in analysis, a breakthrough in combinatorics, and a breakthrough in ergodic theory. So the first breakthrough was initiated by Gowers, and it's called higher order Fourier analysis. It's a new way of thinking, and it basically, the story that it tells is that if you want to prove the Semeridis theorem for higher k, it's not that you have to refine the Fourier analytic technique and then you can do that. You cannot do that by Fourier analytic techniques. Instead, you have to generalize Fourier analysis itself to be able to prove the general case of Semeridis theorem, which is much more exciting because a refinement of a technique is less interesting than actually having a more general theory. So actually, this is a fantastic outcome of this story, that there exists a reasonable version which can be called higher order Fourier analysis, and it's actually good for studying Semeridis theorem. Gowers actually obtained better bounds for Semeridis theorem, and also this higher order Fourier analysis was used in the celebrated Green-Tao theorem that primes contain arbitrary long arithmetic progressions. So this is a fantastic viewpoint. The second breakthrough, which was around 2000 again, is the hypergraph regularity method. The graph regularity lemma is one of the most fundamental tools in graph theory, but the hypergraph version looked much, much more complicated, and in fact, to state it properly and have all the right consequences, we had to wait until the early 2000s when Rödös, Kokan, Nagleschaft independently, Gowers finally managed to develop the hypergraph regularity method. And it's extremely complicated. Papers are very long. And in fact, it was first developed for 3 uniform hypergraphs, then for 4 uniform hypergraphs. I think there was some paper even for 5, I'm not sure, but then the general case was born. So it's a complicated theory, but very powerful. And then the third breakthrough is in ergodic theory. It's a generalization of the Kronecker factors, the higher order generalizations. It was developed parallelly by Host and Krah and Ziegler. And so it turns out that there are higher order versions of this Kronecker factor. I mentioned that the Kronecker factors in some sense corresponds to Fourier analysis, and people actually believed that these higher factors should in some way correspond to higher order Fourier analysis, but it was more like an intuitive correspondence rather than a precise correspondence. But there is a punchline here later, but I'm going to tell you about that. But so all of these things are linked to the Semeridis theorem. They were motivated by them, and there are some common themes, namely the use of uniformity norms. Here there is the host-cross semi-norm, here there is the Gowers octahedral norms, here there are the Gowers uniformity norms. So the uniformity norms are used to measure quasi-randomness or some kind of properties of functions, which are essential in these things. And another interesting thing is that in all of these theories, the notion of a factor in some sense comes up, either in an approximative way or in a precise way. In higher order Fourier analysis and hypergraph regularity, it turns out that there are certain approximate factors in the structure theory of characteristic factors. There are precise factors. So basically there is a moral here. If you want to understand these complex systems, then you want to understand certain simplifications, certain factors which behave in a simpler way. And all of these breakthroughs in this higher order setting centered around understanding higher order correlations in complex systems. So we got used to studying pairwise correlations in statistics and probability theory. Those are the ones that behave in a nice way. But if you want to understand higher order correlations, like say you take the product of 3 random variables and you take the expectation, these triple correlations are much more algebraically more complicated to understand. And in fact, all of these breakthroughs are contributing to understanding these higher order correlations in complex systems. Parallel to this development, there was the birth of structural limit theories, which were motivated by several things, works by Semeridis, Fürstenberg, Oldus, and others. And basically, it was a large program to study mathematical structures, astronomically big mathematical structures using analytic methods. So as I said, already it was present in mathematics, but at the beginning of 2000, there was a systematic program to do that, to understand limits of discrete structures, graph limits. For example, there are these dense graph limit theories, there are bounded degree graph limit theories, and there are intermediate density. It's a very rich universe of things. Then there are other combinatorial structures, hypergraphs. I worked on that with Gabor Elek. Additive structures. I started to develop a limit theory for additive structures. And then people looked at limits of permutations and so on. And finally, I mean, not finally, this is an infinitely long story, but with Agnes Backhaus, we looked at the limits of certain operators, which it's quite funny, but it turned out to be useful in machine learning. So they started to use that in graph neural networks. This whole framework. But here is this roadmap I wanted to show you to these higher order theories. So limit theories, why did I mention limit theories? Limit theories help you with understanding this picture, first of all. So limit theories are used all the time here. And let me do some explanation here. So this is the classical picture, which involves this Kronecker factor in dynamical system. Fourier analysis is a very classical theory. And this yes. So the Kronecker factor is the following. You take this dynamical system, and you look at eigenvectors of t, those functions that if you shift by t, they just get multiplied by a constant. They generate a sigma algebra. That sigma algebra is a factor of the system, which can be given the structure of a compact abelian group. Actually, so basically that system is equivalent with a compact abelian group with a shift. It's fantastic, by the way, that you get all this algebraic structure. And the higher order factors, in the higher order setting, there are these characteristic factors which are given the structure not of compact abelian groups, but more complicated nilpotent structures, some nilpotent things that I may have some time to explain what they are later. Then there is this Fourier analysis. It's obviously it's a very classical old subject, and the non-commutative generalization RT, which is representation theory of compact or locally compact groups. It's very it's known, and actually this connection I will specifically explain later, how Fourier analysis is related to spectral methods. And the Semiredis regularity, I will mention how it's related to the spectral methods. But all these things are deeply connected. They form a bubble. And as I said, the Roth theorem belongs to this classical picture. It's very funny that K-term arithmetic progression case of Semeredi corresponds to the K-2 order theory. So 3-term arithmetic progression is order 1 in a precise way. Actually, Gowers defined it why. This is an order 1 linear form, but for K, for example, the 4-term case is already a quadratic problem. So it's very interesting. So here, the pairwise study of pairwise correlations corresponds to classical picture. Here you have to subtract 1. So pairwise correlation is first order, triple correlation is somehow second order, and higher order correlations. And classical linear algebra deals with 1 and 2 tensors, so vectors and matrices, and here the higher tensors come into the picture somehow. That's related here. And just a bonus that I recently worked a lot on, groups are classical concept, but there are these group spaces which are kind of related to higher homotopy theory. I wrote a paper about that, and they belong to this higher order picture. So, so basically, this is a way of thinking about this whole thing, that there is I talked about Semiredis theorem, dynamical systems, and so on, but there is a much more general thing, which this is not the end of the story. Probably I could write much, much more here. And lots of things are missing. We don't know what the right spectral theory which completes this picture. I mean, there are many spectral theory for higher tensors, but what is the one which relates to higher order Fourier analysis the same way as spectral theory relates to Fourier analysis? There is actually, I have some properties that such a higher spectral theory should satisfy, but it's very interesting. And what is a higher order representation theory? I have some guesses. So it's very exciting. It gives you some hints what to do. But so in a recent paper, so the second part of the talk will be devoted to a much more down-to-earth thing. So the first part of the talk is storytelling, this general high-level picture, and then I will zoom into some very, very down-to-earth particular things, which are cool, I think. But this, the second half of the talk is based on a recent paper that I wrote with Pablo Candela, Diego Gonzalez Sanchez, and this is a new spectral approach to higher order Fourier analysis. You have to somehow spectral methods themselves don't give you higher order Fourier analysis. You have to iterate them in a tricky way, but there is a way of doing that. And so this will actually give some hint probably how this missing spectral theory should look like. Okay, so let's move on. Sorry. So let me just recall what Semeredi partitions are, but in a slightly unusual way. I will do that instead of graphs, I will do them for matrices, and because it's cool, and I will state the Semeredi's regularity lemma in a slightly unusual form. So for a matrix M, I'm going to denote the sum of a submatrix by this. So the UW submatrix is just the sum of the entries in U cross W. And with this notation, if you have and another notation. So I will study matrices which are where the rows and the columns are indexed by a finite set V. Okay? So if you have a partition of this finite set V, then there is an operation which projects matrices to this partition. It's a very natural operation. So MP, this projected matrix at the row X and column Y, the value of that is just the average of the entries of M in this submatrix corresponding to Pi and Pj, where X is in Pi and Y is in Pj. So if you want a picture associated with this, here is your matrix, here is your partition, and basically there is an entry in the original matrix here. This is MXY, but you replace that entry by just the average of this whole submatrix, and you put it everywhere, right? So that's a projected matrix, which is a very convenient concept. You can also define cut norm, that will be important for a matrix, which is you take the sums of submatrices, absolute value, and then you maximize that and you normalize it by the total number of entries. So that's a norm you can check. And the informal version of Semiredis regularity lemma says that for every fixed epsilon, there is some k, such that if you take any matrix, doesn't matter which size, then there is a partition of P, partition P of V into at most k sets, such that this projected matrix is sufficiently similar in the cut norm to the matrix M. So it's basically an approximation theorem that you can project it to a bounded partition and still you can get very similar to the original matrix. More precisely, a technical statement is this, just for those who want to know the details. So if you have an arbitrary decreasing function, by the way, it's stronger than Semiredis original lemma. It's the so strong version. If you have an arbitrary decreasing function, then for every epsilon, there is some constant depending on epsilon and this function, such that if you have an arbitrary bounded matrix, then there is a partition of V into at most k steps. And furthermore, there are auxiliary matrices, ME and MR, so that there is this triple sum. You can decompose the matrix into a structured part. This is the projection of the matrix to this partition. It's bounded complexity because it's just a block matrix with that many blocks. So this is a bounded structure in some sense. There is this L2 error epsilon, it's the normalized L2 norm, and then there is this random part, which can be insanely random in terms of the complexity of the structured part. So you tell how random it should be. You can have your wish list and it's that random. The price that you pay for that is the constant will be bigger. So it's a very cool formulation. And so basically, if you want to get the graph version of Semiredis regularity lemma, then you just apply it to symmetric 0, 1 valued matrices. So the operation which sends M to this projected matrix is basically a dimension reduction. It reduces the graph to a bounded dimensional object by preserving essential properties. This is a common theme in dimension reduction in general. So dimension reduction is very popular recently because of machine learning. Semiredis regularity lemma is basically a dimension reduction, a smart dimension reduction. Okay, so now the regularity lemma in its original form, the strengths of the Semiredis theorem, you may have noticed that there is the arbitrary decreasing function the more it decreases, the stronger the regularity lemma is. And then that this is what I call the strengths. The original formulation had some intermediate strengths, but it's already non-effective how I reformulated it because the constants are astronomically large, 2 to these exponential towers. So that's a trade-off between strengths and effectiveness. Iskanen formulated a weaker but more effective version and so on. I just wanted you to know that for some reason. And then also an important remark is that low-rank approximation of matrices in a non-trivial way, but it's equivalent to graph regularization. I have a paper about that which tells you the correspondence. I call it the spectral regularity lemma. So that's another connection with dimension reduction. And also it connects because low-rank approximations are related to the dominant eigenvalues. This connects regularity lemma with spectral theory in a very crucial way. And moreover, I will talk a little bit more later about that deep connect. There are deep connections between Samaridis regularity lemma and the principal component analysis. Okay, so, but what about generalizations of the regularity lemma? Can you find useful dimension reductions for other structures in mathematics? And I mentioned hypergraphs. Those are doable but hard. And what about additive structures? So the hypergraph regularity method is now here by Röders, Kokan-Nagle, Schacht, and by Gowers. And with Gábor Elek, we worked out a different approach to the hypergraph regularity method, which is based on non-standard tools. And it can give you new theorems, new finite theorems, surprisingly, although it uses ultrafilters. But it leads to new finite theorems about the regularity method, and it gives you a new viewpoint where in this infinite limit somehow the regularization just becomes a certain factors of measurable structures, more analogous to the Fürstenberg approach. So it's already a cool connection. And also I started to work back in 2009 already on arithmetic regularity lemmas, and this is a big story. Green-Tao Ziegler formulated such lemmas. I think I was the first one who formulated such a lemma and for general Gowers norms. And with Candela, we have a paper which summarizes what we know about that. So basically, writing arithmetic regularity lemmas is more or less equivalent to higher order Fourier analysis. I have to add more or less to this because it's not precise. The next remark is that I mentioned that regularity lemmas are connected to dimension reduction. But dimension reduction, when you approximate arbitrarily big structures by bounded structures, leads very naturally to similarity metrics. Because once you have this dimension reduction, you can compare different structures of different sizes. Two structures are similar if they have a similar dimension reduction, okay? And that naturally leads to structural limit theories. I would even say that structural limit theories and dimension reduction is the two sides of the same coin. And this is really how it works in practice. So there is this interesting triple correspondence between regularity lemmas, dimension reduction, and structural limit theories. Yeah, I mentioned already connection to machine learning, that low-dimensional data representations are actually crucial. They appear naturally in neural networks. So let me tell you my first secret. It's not such a big secret. This is already in my paper. So we managed to understand an algebraic skeleton of how regularization in general works. And this is a common theme in all my work. So basically, what you have is that you have some structure, graphs, hypergraphs, additive structures. These structures are can be typically represented by some function on a more homogeneous space. So, for example, Graphs are just functions on product sets, V cross V. That's a graph. A hypergraph is a function on larger product sets. Three uniform hypergraphs is a function on V cross V cross V. I mean, that's uniform hypergraph, sorry. And then an additive structure is a function on an abelian group. So the ground space is some very homogeneous algebraic structure. You have a function. That's the analytic part of the theory. And then what regularity really means is that you have some kind of a representation, a low-dimensional representation of this algebraic underlying ground space to something which depends on what type of structures you want to study. So there is some emergent algebraic structure and a bounded dimensional representation, such that if you look at this composition of these morphisms, this is typically a morphism between algebraic structures, some homomorphism or whatever, and G is again some analytic function. E is already can be some kind of a topological space, but bounded dimensional, and G is some Lipschitz function. And then what you want to achieve is that you want to approximate F, the original function, by this composition, which factors through this low-dimensional representation in an appropriate uniformity norm. So this is a general scheme for regularization. It's kind of an approximation through this algebraic part, which is some morphism, and also composed with this analytic part. Funny enough, but the hypergraph regularity lemma with Omar Antolin Cameron, he was a master's student of mine in Toronto, we realized that the hypergraph regularity lemma fits into this framework. You have to use certain delta complexes. Those are the emergent structures to complete this picture. But that's one example. But I want to also tell you that higher order Fourier analysis fits into this picture. And I want to tell you a little bit more about higher order Fourier analysis. This is the crash course. Okay, Z in this talk is a finite abelian group. You may even think of it as the cyclic group, doesn't matter. Already the cyclic group is interesting enough. And then one can introduce this multiplicative derivative of a function where you take a shift of a function and you multiply it with the conjugate of the function. That's the t derivative. And the Gauer's norms arise from iterating that for a function f. You take these multiple multiplicative derivatives, k-fold multiplicative derivatives with t1, t2, and tk. No, not necessarily. These are complex valued functions. And then you iterate this and you take expected value over everything, the function value, the t's, everything, and then you take this appropriate root, and that turns out to be a norm. Very beautiful statement by Gauers. The U2 norm is nothing but the L4 norm of the Fourier transform. So you take the sum of the fourth powers of the Fourier functions and you take the fourth root of that. So if f is smaller than 1 in absolute value, then you have this inequality that the U2 norm is basically can be bounded from below and from above by the L infinity norm of the Fourier transform, which means that the U2 norm is close to 0 if and only if f correlates with a linear character. Because if and only if U2 norm is not close to 0. If it's not close to 0, then the L infinity norm has to be significant, and then there is a Fourier coefficient which is significant. So this is what it measures. But in higher order Fourier analysis, we address this question of what does FUK measure. So the U2 norm is related to ordinary Fourier analysis. The UK norm measures something mysterious, and here is a philosophy of how you have to think about all of these things. And the philosophy is that if UK norm is 0, then we think of f as k minus 1 order noise, so quasi-random. If f is orthogonal to order k noise, then we think of f as kth order structured function. If delta t f is of order k minus 1 structure, then we think of f as a kth order harmonic function. For example, zeroth order functions are constant functions. So if these multiplicative derivatives are all constant, then f is a multiple of a linear character, and then it's actually a classical harmonic function. So soft regularity is a decomposition into noise and structured parts in this setting. And this is what I call soft regularity for this talk. And structural regularity is when you give an algebraic decomposition of the structured part. So you start with a function. You want to decompose it into two parts first. Generally, it's more complicated. The one part is a noise, so it has a small UK norm. The second part has to be structured. And if you can say something algebraic about the structures, then you are even happier. Okay? So the difficulty is that all of these notions are approximate. So this actually, it's a real difficulty, and you have to fight with certain epsilons in this theory, but an idealistic non-approximate version of this theory appears in the ultra limit, which is very helpful to think about that. There is a Platonic picture behind all of this, which is a perfect picture. But so the question arises, can we generalize Fourier decomposition, Parseval's identity, and all these classical things from Fourier analysis to this higher order setting? Now, because I don't have too much time, I have to skip some parts of the talks. I actually overestimated my time. So I just wanted to briefly mention that we introduced with Omar Antolin Cameron a set of algebraic structures with very simple axioms that we call the nil spaces. And these nil spaces, very prominent examples for them come from the Heisenberg group. It's a cool thing. If you take the upper triangular 3 by 3 matrices, and you take this subgroup of upper triangular integer matrices, there is 0 everywhere below the diagonal, then this is an example for a 2 nilpotent Lie group and a co-compact subgroup. And if you take the vector space, that's like a 3-dimensional compact manifold, which has some extra algebraic structure on it. And you can make those things nil spaces. Those are one of the most fundamental examples, but there are other examples. So the big program that we recently kind of finished, basically, is that we worked out the whole regularization picture in this setting where the algebraic structures are certain Lie versions of these nil spaces, finite dimensional nil spaces. There are continuous morphisms from compact or finite abelian groups. So there is a representation theory appearing where the target objects are these nil spaces. So non-commutativity appears already when you study stuff on abelian groups, on commutative groups. Non-commutativity appears as an emergent phenomenon. That's one of the most fantastic conclusions in higher order Fourier analysis. And this target object together with this function, you can think of it as an approximate model of the original function, which has similar algebraic properties. So this is, there are many papers which led to here. I just mentioned the last 4 in the memoirs, the Krell and the dynamical systems. And some papers haven't even appeared yet. But anyway, so this large program, which I've been doing for a long time now, is basically completed, more or less. There are still open questions. I want to mention that what this paper does, this first one, is also gives a new proof for the characteristic factors of dynamical systems, the structure theorem for the characteristic factors, even in a more general setting where you consider arbitrary even nilpotent groups, not just abelian groups. So it's not just for Z actions, but for arbitrary group actions. And it actually connects, it gives a precise connection between higher order Fourier analysis and dynamical systems. So this is one of the punchlines that you can actually, there is a unified theory which connects these two. Okay, I skipped this slide because I don't have time. I want to get to the actual very down-to-earth part. So if you have slept so far, wake up because you will understand this in the remaining few minutes that I have. So Fourier analysis is obviously useful. There is a fast Fourier transform, which is very effective. It is considered to be as one of the most important algorithms of our lifetime. It's definitely ranked in the top 10 most important algorithm. So it's a very important algorithm. It's used everywhere. And the main question is higher order Fourier analysis similarly useful in practice? Not even in mathematics, in real life. I mean, that's a very natural question. And people didn't care that much about that so far. There are applications, but like applications in mathematics. So there is this book by Terence Tao I highly recommend. And then there is this book which focuses more on theoretical computer science by Hatami and Lovett. But these are not like real-life applications. These are applications in mathematics or computer science. But in applied mathematics, there is virtually no application. I say virtually because I can never know, but I haven't seen any application. There are algorithms by Tulsiani and Wolf. They introduced these quadratic analogs of the Goldreich-Levin algorithm and so on. So there are algorithms. They mostly are probabilistic, iterative, and work in the finite field setting, which is of central interest in theoretical computer science. But in signal processing, you want to know more of time series and more down-to-earth objects. Okay, so major question, are there algorithms in the field of higher order Fourier analysis that are useful in applied mathematics, similarly to the fast Fourier transform? I mentioned that higher order Fourier analysis has an approximate nature, which makes it harder. But nevertheless, I am going to actually define you an algorithm which we analyzed, and it looks extremely promising. So, but first, let me explain to you what are the spectral aspects of ordinary Fourier analysis. I want to tell you something very elementary. So if you have a finite abelian group, and you have an operator, a linear operator, on the function space of this group, so a matrix, a Z by Z matrix, basically, which commutes with all the shifts, then it turns out that the eigenvectors of this matrix have to be the linear characters. So this is a direct connection between spectral theory and Fourier analysis, and the proof is extremely simple. I wrote it out here. I don't really have time to read it aloud, but anyway, so it's a super simple proof. And if you think about that, what does it mean that the operator M, the matrix, commutes with the shift? So if you have such a matrix, Z cross Z matrix, so rows and columns are indexed by the elements of the abelian group, then we can introduce the notion of a T diagonal of M, which is the set of entries where the difference between the two indices is fixed. So it's basically the set of entries mi plus t and I, these diagonals. So basically, this is what you can, what you would imagine, that here is the matrix, Z cross Z matrix, and you have this cyclic diagonal. And the matrix can be decomposed into the union of these diagonals. And if you look at the diagonal itself, it behaves like a function on Z already. So every matrix is a collection of functions. But if all those functions, if M commutes with all the shifts, that's equivalent with saying that all those Z diagonals are constant functions. Okay, that's a trivial observation. And the spectral aspect of Fourier analysis goes deeper than that. if you take any function on an abelian group, and you form this rank 1 matrix, which is just F times the F adjoint, so this column vector and this row vector, you take the product, that's a rank 1 matrix, and if you average out all the Z diagonals, then it turns out that the eigenvalue of a linear character of M is just the Fourier coefficient squared. So basically this is this connects spectral theory with Fourier analysis. You start with a function, you create this rank 1 operator, then you make it Z invariant, you average out all the shifts of this operator, and then you look at the spectral theory, and the spectral theory will give you essentially back up to phase the Fourier theory of F. Okay? It's really cool. But also, it's an interesting observation that the T-diagonal of this function, of this rank 1 matrix, is this multiplicative derivative. You can just calculate. It's a trivial thing. So, by the way, the connection to principal component analysis is that basically what it tells you is that if you have shift invariant data set, then principal component analysis is just equivalent to Fourier analysis in some sense. So that's just, I wanted to make this connection. But can this be generalized, this picture, this correspondence between spectral theory, PCA, and Fourier analysis, can this picture be generalized to higher order? That's the question. And indeed, what we found that there is a machine which does that. It's the order increment principle, a very simple and very elementary machine, which turns case order Fourier analysis into k+1 order Fourier analysis. There is something to iterate here, though. So basically, you take a function on an abelian group, you form this rank 1 matrix, F tensor F bar. Then you look at these order k diagonals as functions, and you do so-called order k regularization. You just delete the random part and you keep the structured part for each of those diagonals. Then you get a new operator. You look at the spectral theory of that, and that will basically encode k+1 order Fourier analysis. That's the order increment principle. Let me repeat that a little bit slower. So you want to understand the function on an abelian group. You create this rank 1 operator out of the function, F tensor F bar. Then you kind of do case order Fourier analysis for each diagonal, okay? And if you do that, and then you look at what you get, that's a new operator, and then spectral properties of that new operator, then you get k+1 order Fourier analysis. More concretely, in the quadratic setting, I need to do on this diagonal something which I call Fourier denoising, which is interesting on its own right. It's again very elementary. It's classical Fourier analysis. You take a function on an abelian group. And what I want to achieve is that I just want to preserve the structured part of F. I want to remove the randomness from F. What it basically does is that small Fourier coefficients have to be kind of removed from the function. You could just say, the most trivial thing would be just to say that we look at all the Fourier coefficients. If a Fourier coefficient is smaller than epsilon, I just cut it off to 0. That would be the most trivial thing. But the problem with that is that it has bad properties. It's not continuous and it's a bit ugly. So instead, what we do, we introduce this Fourier denoising operator, which behaves in a much better way, where I keep the phase of each Fourier coefficient, but I basically move. So here is a complex number. We are on the complex plane. Here is a complex number. I keep the phase, but I move epsilon back towards the origin. If it's shorter than epsilon, then I just move to 0. So I just shorten all these Fourier coefficients by epsilon. And by the way, an interesting high school problem, which is not so simple as it seems, that this distance will decrease. So it's a contraction in L2. Just give me a very, very simple proof for that. It's not so simple. That if you do this kind of, basically, it's the problem in a high school way is that there is this campfire and two people, A and B, are standing somewhere and they both move epsilon towards the campfire. They get closer to each other. Obviously, it's not true if this is they move different amounts. Then if this moves more and this moves much less, then they get further from each other. But if they move exactly epsilon, that's a contraction. It's a nice high school problem, actually. Just think about it on the plane. Anyway, so that's a contraction that we introduced. And that's we call Fourier denoising if you apply it to the Fourier coefficients. And then the algorithm is that just you do that operation in each diagonal. So once more, let me repeat the very simple algorithm, very down-to-earth thing. You start with a function, then you take this rank 1 function, and I can even draw this. So but this rank 1 function is that here is the matrix, rows and columns are indexed by Z. You put here F, you put here F bar. So the matrix is just basically Fx times Fy bar, okay? That's a rank 1 matrix. You take these diagonals and you do this Fourier denoising in each diagonal. Very simple thing, and you get a new matrix. So my order increment principle tells me that this new matrix should be related somehow to quadratic Fourier analysis, and indeed we could prove that. But before doing that, let me give you a funny example. So actually this is just a window from a larger abelian group. I took Z to the 500, and I took this function which has a quadratic structure. Obviously there are much more complicated functions with quadratic structure, but this is a simpler one. That doesn't have to be of this form if something is quadratic. It doesn't even wrap around nicely numbers theoretically. But nevertheless, so this is the function of the green dots. And I added a huge random noise to this function. So those are the red dots. It's this random fluctuation. And then what we did is that if we take this operator, you look at the dominant eigenvalues, and you project F back to the subspace generated by the eigenvectors corresponding to the dominant eigenvalues. That is something like principal component analysis, but now we are in the quadratic setting. And if you do that for this particular operator, you get this quadratic denoising algorithm. And quite miraculously, you can see that, so if imagine that you just get this function of the red function, and suddenly this recovered this original function with a very good precision, which is quite a miracle, actually. We didn't expect this to be this good. But nevertheless, so it looks like a very practical algorithm, which has a very reasonable complexity. So we are testing this algorithm. The fantastic thing is that it can be parallelized very efficiently, and recently this is very much doable because of the good hardware developed for machine learning. Because in each diagonal, you have to perform a fast Fourier transform to do this truncation, but you can do that parallelly. So basically, the complexity of that is if you can do it parallelly, it's a single fast Fourier transform plus the spectral decomposition. Okay, you have to do an inverse Fourier transform. And the spectral decomposition, you just need to have the dominant eigenvalues, the few dominant eigenvalues, which is even faster than getting all the eigenvalues. I don't want to go into the details because I don't have time, but I just wanted to say that, yes, the whole thing runs very fast, reasonably fast. And we did a lot of experiments. We are actually writing a completely applied mathematical paper about that. But we formulated a complicated theorem, which is the theoretical background of this thing. And actually to prove this theorem, which gives you why this actually does what it should do. So this is a 70 pages long paper. and it actually proves new results in higher order Fourier analysis. It works out a spectral approach to higher order Fourier analysis. So it has a lot of theory in it. This paper and the proofs are heavily based on this whole nil space theory and regularization, which is another, I would say, 300 or 400 pages literature. So I am saying, actually, once I gave a talk about this, and the title was that surprisingly simple algorithm with a surprisingly complicated justification. So you have this very simple algorithm. It runs very fast. It's very good. But to justify and even to understand what it does, we don't have anything simpler than all this literature. Maybe somebody will come up with some simpler explanation. We could not. And basically, this is the end of my talk. I have no time for this further slides. So thank you very much.
So I guess the example that you gave was, right, you take some function like sine and apply it to some quadratic polynomial. So if you want, so these are the kind of things that this is very good at recovering, right, this algorithm.
But not just that. There are more complicated functions.
Do you find, are there such things that you found in real life that are of this structure?
So that's a very good question, because so we understand how this topic is related to dynamical systems. So basically the connection is this. If your data is produced by a complicated dynamical system, say solar activity or something, weather, and the dynamical system has a second order factor, a non-trivial second order factor, then very likely it will show in the data that it produces. And then there will be some kind of non-trivial quadratic component of the function that you can isolate. So basically the moral of this should depend on the dynamical system, on the structure of the dynamical system that produces the data. This we understand.
So maybe we can learn some new things about even this data, some new aspects that we have never considered before. Interesting, and you could compare it between, say, different data sets, what they relate.
Exactly, it digs a bit deeper into the structure, because people use Fourier analysis to find the frequencies, but this finds this kind of more complicated irregular frequencies by, yeah.
There are more questions? If no more.
Dynamical system, there is one-dimensional time. You iterate some map, or there is one-dimensional time. But there are higher rank actions when you have kind of multi-dimensional time. Is it fair to say that what you're discussing would be related to this type of dynamical systems, where you have kind of commuting maps and then you can commute them in different order, so it would correspond to two-dimensional time, three-dimensional time?
So what we know is that, so as you said, so Hoskra-Ziegler theory is originally the original papers about Z system. You have a single transformation. And then this can be extended, for example, with Pablo Candela, we extended that to arbitrary commutative actions and even to nilpotent actions. So that still works. Many people actually, Tao and co-authors also work on extensions of these things to other groups. Yes, so if the group is abelian, then higher order Fourier analysis is still relevant. If the group is not abelian, I know much. I mean, not even nilpotent. I know much less about that. I don't know what happens there.
Abelian.
Abelian groups, or at most nilpotent groups.
Is there more question? If no more question, we can thank the speaker.